Up to now, I presented scheduling algorithm with respect to the single CPU. What if our system has multiple CPUs? My explanation, my introduction of the various scheduling algorithms still valid with respect to the multiple CPUs? Let's talk about it. And there are two popular ways to assign processes to and multiple CPUs, or cores, and this circle represents CPUs, by the way, and or core. And this technique is, as you can see, each CPU, they have their own local queue. And this technique is known as some types of supermarket, like a market counter, and or bank. If you go to the bank, and each banker has their own queue, right? You need to line up in one particular queue. And what's the problem? The problem is if you just standing on a particular queue, let's say here, and one of the person in front of you take forever, then you may end up stucking on this queue forever, right? That is a downside of having the local queue. And so to resolve that problem, then you can have one global queue, which is shared by all the CPUs. That means whoever available, whoever or whichever CPU available, then whatever process in front of you can be dispatched immediately, right? So those local problem can be resolved by having one global queue, okay? And however, the problem is because this one single queue is shared by the multiple CPUs, therefore, and this queue need to be like the consistencies of the global queue need to be maintained. For that reason, and this single global queue need to have some kinds of lock and unlock. So this is a critical section, and I will cover this topic later. Since this global queue needs to be shared by the multiple CPUs, whoever tries to update this global queue need to lock this queue and unlock this queue. Therefore, the number of CPUs increase. This global queue turns out to be the focal point of contention, and that requires lock and unlock frequently. Therefore, as there will be a serious slowdown on this single queue. And XV6 actually use the technique for the single shared global queue. By the way, and if you are the careful people who navigate or explore the XV6, XV6 handle two CPUs, CPU 0 and CPU 1. And I will show you the code on the next. And as you can see, the CPU 0 and CPU 1, they fight for the single global queue. So the problem of local queue per CPU is it can lead to imbalance. That means even though there is several available CPUs, but if you stuck on this queue, then you cannot be easily assigned to these available CPUs. The reason is, and the process in front of you, the customer in front of you, just take forever to be serviced. And so that's what I meant by the local queue can lead to imbalance. And this problem can be solved by having single shared global queue, and this process from this single global queue is dispatched immediately whenever there's available CPUs. However, accessing queue can be the bottleneck, because whenever you update this queue, and this queue needs to be locked, otherwise, and the state of this single queue can lead to the inconsistency. So therefore, and the single shared global queue, accessing queue can be the bottleneck. This is a serious issue. Obvious variation is having the local queue and global queue together. So why they having these two queues? And as you can easily tell, they try to make the best of the benefit of local queues and global queue. And so what is the local queues? And the local queues is used when you assign certain high priority processes, then they can drop into this local queue. In other words, and when certain process you would like to run on a particular CPU, then local queue will be used. And otherwise, if certain certain process arrive, which turns out to be not that important, then they will stay on this global queue. Then the CPU will try to run whatever job from this local queue, associated local queue. If there is no processes, then they grab the process from the global queue. And turns out to be, and this technique is implemented by the early Mach operating system. So as you can see, each CPU, each core, they have their own queue. And whenever there's no process to be scheduled on this CPU, then they grab the process from this global queue. And so this is the diagram to represent the variation, which is local queue together with the global queue. And so as you can tell, there should be some value to have this local queue, right? So let's take a look. And that can be understood by explaining the scheduling algorithm for the multi-CPUs. There are 3 thread scheduling strategies, and one is a static assignment. And so thread always assigned to the same CPU. And you may wonder when this happens, and I will explain later. And the other one is dynamic assignment. This is the single shared queue, global queue. That means whatever thread and throw into that global queue can be assigned to any CPU. And this is known as dynamic assignment. And the third technique is the dynamic load balancing, and which is the most complex scheduling strategies. That means threads can move between queues. And as we talked about the local queue, whenever we maintain the local queue, and what was the problem? When we stuck on one queue, then in spite of there are other CPUs can handle that, but you cannot assign to that other CPUs, right? So in order to resolve that particular imbalance, dynamic load balancing can be placed. That means threads can move between queues, and whenever certain other CPU, their queue is empty, then whatever thread that sitting on the other queue can be moved to this empty queue. And turns out to be the Linux use this approach. And this is the most general scheduling strategies. However, as you can tell, this introduces quite a complexity to the kernel scheduler. So you may wonder when the static assignment, in other words, when a thread always assigned to the same CPU, what is the occasion, right? And so let me talk about it. So in the case of kernel threads, right, and kernel need to be and quickly service the user request. And in that case, the kernel thread is known as a master, okay? That means kernel thread always run on the same CPU as a master. So we, in the presence of multiple CPUs, and one CPU is dedicated as master, and this CPU will only run the kernel threads only. And so all the rest is a slave. That means they can assign to any CPUs. And as you can tell, there's other contrasting approach for the multiple CPU is a pure approach. Any thread, kernel, or user, doesn't matter. They can run on any CPUs. Okay? And so this is kind of the 2 contrasting approach. And so what I would like to talk about is, then what's the use of all these scheduling algorithms that I introduced? And it's still valid, right? The reason is each CPU, let's say quad core, and they have their own local queue. And also they have one global queue, right? And the scheduling algorithm that we studied so far, still valid. The reason is, and this queue can be implemented as a multi-level queue or priority queue, and this queue can be managed in different technique. It can be FIFO, and it can be shortest first or whatever, right? So all those scheduling algorithms that I talk about for a single CPU still valid. The reason is each CPU, they maintain their own local queue together with one global queue. So the system can be as complex as possible. They have the different queue management strategies for the global queue and local queue. In master-slave approach, key kernel threads always run on master. And so what is the pros? And this technique is simple and easy to extend the uniprocessor-based kernels. In other words, when you design and implement the kernel on a uniprocessor-based system, and it can be easily ported to the multiprocessor because the kernel threads, the key kernel threads will be dedicated to one CPU. Therefore, the porting of the operating system to multiprocessor or multiple cores is relatively easy. Obviously, the downside of the master-slave approach is, what if all threads making the system calls, in other words, there are bursts of the request to the kernel service, then the master node, best CPU, can be the bottleneck. And this is, the second one is the kinds of problem of any types of distributed system. What if master fails? Because this is the focal point. So if the master fails, then the entire system fails. That is the downside of the master-slave approach. So in PO approach, and each CPU does its own self-scheduling. And as I said, each CPU, they have their own queue. And this is the way the thread is scheduled. And there's also one global queue. And whenever the queue is empty, and they can, whatever thread in this global queue can be assigned to any available CPU. So this is the PO approach. In other words, there is no dedicated CPU for any types of threads. And since each CPU does its own self-scheduling, and also the pros is load balancing. As I said, if the thread is stuck on one queue, and if there's any available CPU, then this thread can be migrated to the other queue, and by doing that way, it can achieve the load balancing in PO approach. And also, there is no one dedicated CPU to run the kernel thread, important key kernel thread, and since those threads can run on any CPU, therefore, in spite of one CPU is fail, and it doesn't gear toward the entire CPU system is failure. So there is no single point of failure, therefore it is fault tolerant. And the downside is complexity. And to maintain this multiple queue with the different strategies is quite a nasty code. So therefore the system gets unduly complex. And the other one is, since whenever you're migrating the one thread to the other queue, and that means the queue can be updated by the multiple CPU. That means we need some kinds of locking mechanism, therefore, and must be careful about the synchronization, which I'm going to talk about in the next section. It is a dominant trend in computer industry. They provide the system with a large number of CPUs. And if that is the case, then when a thread is assigned to run on a particular CPU, and just leave it there until it is done. That means even if the certain thread is a block for I/O system call, don't do any context switching. Just leave it there until it complete. And there's another technique. So when you have some cooperative, the groups of related threads, and just assign those group of threads to the CPU as a group instead of the single individual. By assigning the group of related threads on a CPUs, by doing that way, and those cooperative threads can interact fast enough, and also in addition to that, there is no need for the context switching. Therefore, it can lead to quite high performing application. And sometimes the problem is wasteful. Okay, maybe some CPU can be wasted or idled while it is waiting for some types of I/O. But it is okay. And we have some different problem. The problem is we have large number of CPU. Our problem is underutilization of CPU, not the overloading of the CPUs. So the wasteful in this environment, it is okay. When a CPU becomes available to execute a certain thread, and the question which thread we need to assign, this problem is known as thread dispatching. For uniprocessors, and thread selection make a big impact on the system performance on a uniprocessor. And that was the reason why we studied many various scheduling algorithms, including the multi-level feedback queue and priority queue scheduling and stride scheduling and so on. So we have variety of complex scheduling algorithms. Since for a uniprocessor environment, whatever thread selection as a dispatching decision make a big impact on the system performance. However, when we consider a large number of CPUs or cores, then those complex scheduling algorithm is tapered away. The reason is now our problem is underutilization of the huge number of CPUs and cores, not the underutilization. Therefore, we can afford the waste. If that is the case, then we can use a simpler algorithm. Even FIFO works good. Okay? And simple algorithm, because we can assign a group of threads to the huge number of CPUs, therefore there will be less overhead because we use a very simple scheduling algorithm. And scheduler can assign a group of related threads to the CPUs. Therefore, there is no context switching, can improve process multi-threaded performance even using the very simple scheduling algorithm like FIFO, first in, first out. There is quite interesting experimentation, and let's compare two configurations. One is single fast CPU with a single queue, and let's say this speed of the CPU as a 4 GHz as an example. And how about the other configuration? We have the dual core, each run as half of the speed, which is a 2 GHz. And they have their own local queue. And the question is, which runs faster? And it turns out to be, and the first option, the first CPU, one CPU with a global queue works the better. And based on the experimentation, it turns out to be the half of the CPU seems wasted, and therefore, according to the experimentation, as I said, the first configuration known to work better in the real workload setting. Since the waste of this configuration comes from the imbalance of the size of the queue in the workload, therefore, and this problem may go away by having one single global queue. So how about this? So by having the one single global queue for these slower CPUs like this, then in spite of there are certain thread is long-running thread is waiting in front of you, then you don't need to wait for long time for this configuration, because those long thread is scheduled to this one, and all those short thread can be scheduled to the other available CPUs. So by doing that way, and the problem that I reported in the previous slide may go away. If this is the case, and which works better? And the experimentation report, and there's no difference when it is dealing with average turnaround time, which is a metric that we use to compare the performance of the scheduling algorithm. However, when we consider the other metrics such as a variability, what is a variability? The variability is a variance of the service time of a thread. So let's look at this one. Let's say this thread is a long thread, okay? Let's consider this, the first configuration. Then, and all the subsequent threads need to wait until this long thread finish on this CPU. And so, depending on which thread is sitting in front of you, there's a lot of variance of the service time. However, if you're looking at the second configuration, in spite of the long thread is sitting in front of you, and this thread may assign to this CPU, and all the subsequent threads sitting behind can go to the other CPU. Therefore, the variability can be reduced compared to the first configuration. And the variability can greatly reduce as the numbers of the CPU getting larger and larger. And this is a very important figure, and at the same time it is insightful to studying the operating system scheduling algorithm. So the x-axis is the coefficient of variation. In other words, standard deviation of the variability that I discussed in the previous slide. And the y-axis is the round-robin performance over the first come, first serve. And first come, first serve is the simplistic scheduling algorithm. Whatever first arrive, and that will be the first one that will be assigned. That is the first come, first serve. And round robin is the this is kind of give some time quantum, time unit, and then they just kind of circle around. That is a round robin. So round robin is a little bit more complex than the first come, first serve. And this y-axis is the performance comparison of round robin to first come, first serve. And so let's look at this one. On a single processor, oh, by the way, so when you have the x-axis has a smaller value, that means there is no variation. You know, the standard deviation is a 0, right? That is whatever variation that you feel, and that will be consistent. And that is what I meant by the variation. So whenever your thread is scheduled, then the turnaround time is always identical, regardless what thread is sitting in front of you. That is what I meant by the standard deviation of the variation. So now, let's look at this one point. This is for the single processor. And if the standard deviation of the variation is around 2 point something, and let's look at what it means. In this case, for the single processor case, and the round-robin scheduling algorithm works about what? Maybe 7% better than the first-come, first-serve scheduling algorithm. However, when you're looking at the dual processor, right, and the performance benefit of round-robin scheduling for the dual core is about 1.2, okay? In this case, is about 2% is better than the, so in other words, round-robin scheduling algorithm, and it is about 2% better than first-come, first-serve. But for the single processor, it's about 7% better than the first-come, first-serve. So what is a good lesson? That means when you have like more CPUs, such as like a quad core, or 8-core, and oct-core, just name it, the number of processors increase, then the scheduling algorithm, such as round robin over the first come, first serve, is even less. So that means what is a lesson from this figure? That means when you have large number of CPUs, then scheduling algorithm doesn't matter that much. That is this figure is representing. And surprisingly, this figure is prepared in 1981. Isn't this amazing? I already hinted a scheduling algorithm in the presence of the many CPUs or many cores, that is, schedule a group of cooperating threads to run simultaneously. And let me give some formal name. This scheduling technique is known as gang scheduling. And in this case, the cooperating threads depending on each other. So in that case, either run all or none. So that means as long as all threads can be assigned to the CPU, then it is assigned. Otherwise, they wait until the available numbers of CPU for holding this group of cooperating threads to the schedule. Otherwise, just all or none, right? This technique is known as gang scheduling. Like the gang scheduling, and there's another variation, which is dedicated process assignment. That means dedicate a group of CPUs to a multi-threaded process. So in this case, when a process is scheduled and each thread is assigned to a CPU dedicated to that thread until process complete. So this is a little variation of the gang scheduling that I presented in the previous slide. Why the gang scheduling and dedicated CPU scheduling algorithm works good? The reason is now we are dealing with a different problem. In old days, we're dealing with lack of CPU, right? Now we're dealing with the very large number of CPUs. That means our problem is how to use all of these resources, right? And so we're dealing with a different problem. That's the reason why the gang scheduling and the dedicated CPU scheduling works the better. And why? Because we don't need context switching. There is no reason why we need to switch one thread over to the other thread to share the CPU. And the problem is not sharing the CPU, but the how to use available CPUs. And since we don't have any context switching, therefore the thread never waits for another ready thread. That means every threads are running. Isn't it the kind of happy moment? So again, and the gang scheduling, dedicated CPUs for a process only works when we have very large number of CPUs, which are the norm for the current computing industry. And this is the typical configuration of the modern computer. Modern computer comes with multiple cores, such as in this case, 8 cores. Each core, they have on-chip memory, which is high-speed memory, which is L1 cache. Underneath, they have a L2 cache, the sharing those like a fast memory across the core 0 and core 1. And underneath, there's a L3 cache. This L3 cache is also the fast memory, slower than L2 and L1. However, there's still fast memory that is shared across all the available cores. Underneath of L3 cache, we have a main memory, which is a slowest memory. And this is the kind of typical configuration of the modern computing system. Then this L1 cache and L2 cache is kind of built up while your program is running, and there's a very much good information will be loaded onto L1 cache and L2 cache and so on until there's a context switching. Once the context switching happens, then all the good information has been built on this local memory will be wiped out or trashed. And that's the hidden cost of context switching. So the cache affinity. So we dealt with the gang scheduling and the dedicated CPU scheduling. What is good about this scheduling algorithm? Even though there might be some waste of CPUs, however, and this gang scheduling and dedicated CPU scheduling, at least they maintain the good information on this L1 and L2 and even L3 cache by avoiding the unnecessary context switching. So that's the reason why the cache affinity is served as a good reason why the gang scheduling and dedicated CPU scheduling works good in the presence of huge number of CPUs. And this turns out to be the norm of the modern computing system. So this is the end of the lecture for the scheduling algorithm for the multiple CPUs or multiple cores. So overall lesson is what? When we're dealing with huge number of CPUs, then the actual scheduling algorithm, the complexity of scheduling algorithm is taper down. In other words, it doesn't make much differences, right? That is basic lesson that we learned in the presence of huge number of CPUs, huge number of cores, which are the norm of modern computing system. Then why are we studying the scheduling algorithm, right? And because you only see the one spectrum of the computer industry. We have other spectrum of computer industry, which is embedded system and real-time system. And the next lecture, I will cover the scheduling algorithm for that industry, real-time or embedded system. That's the reason why we study all the complex scheduling algorithm in the beginning of the scheduling lecture.